The launch of Voyager 1 marked a major moment in the development of space exploration carried out by NASA, when a carefully planned mission was prepared to study the outer regions of the solar system. The spacecraft was sent into space in the year 1977, during a period when space science was developing rapidly and when new engineering systems were being designed to allow machines to travel far beyond Earth. The purpose of this mission was centered on scientific investigation of the planets located in the outer region of the solar system, along with their moons, rings, and surrounding space environments. The preparation for this launch involved years of design work, testing, and coordination among many teams working on instruments, propulsion systems, communication systems, and mission planning. The spacecraft was built with a structure that carried scientific instruments designed to collect data about particles, magnetic fields, radiation levels, and visible images. These instruments were installed carefully so that they could function during long periods of operation in space. The design also included a system for sending information back to Earth using radio communication. This communication system depended on large antenna structures that allowed signals to be transmitted across vast distances. The signals were received on Earth by tracking stations operated as part of a global network that continuously monitored spacecraft activity and maintained contact during different stages of the mission. The launch process took place using a powerful rocket system designed to provide the necessary force to lift the spacecraft away from Earth's surface and into space. The rocket carried the spacecraft through different phases of flight, beginning with ignition on the launch pad and continuing through stages of separation as fuel sections were used and detached. Each stage of the rocket played a role in increasing altitude and velocity, allowing the spacecraft to reach a path that would carry it toward its planned journey through the solar system. The timing of each stage was controlled through precise calculations and automated systems that ensured the spacecraft followed the correct trajectory. During the early phase of the mission, after separation from the rocket, the spacecraft entered a controlled path that allowed it to begin its journey toward the outer planets. At this stage, engineers and mission controllers at NASA carefully monitored all signals received from the spacecraft to confirm that its systems were functioning properly. The spacecraft's instruments were activated gradually so that each system could be tested in the space environment. These instruments included devices for imaging planets, measuring charged particles, and recording magnetic field activity. The mission was designed with a primary focus on the study of planets located in the outer solar system, including Jupiter and Saturn. These planets were of special interest because of their size, structure, and complex systems of moons and rings. Scientific teams prepared observation plans that would allow the spacecraft to collect detailed information during its approach and passage through these planetary regions. The instruments were programmed to take measurements at specific times, ensuring that data would be collected during important phases of planetary encounter. The journey of Voyager 1 required careful navigation planning. The spacecraft followed a trajectory that was determined using mathematical calculations based on gravitational forces and orbital mechanics. Engineers used these calculations to design a path that would guide the spacecraft through regions where it could observe multiple planetary systems. The mission trajectory was adjusted during the early phase using small propulsion corrections, which helped maintain the intended direction and ensured that the spacecraft remained aligned with its planned route. Communication between Earth and the spacecraft was maintained through radio signals transmitted over very large distances. These signals were extremely weak by the time they reached Earth, requiring highly sensitive receiving equipment to detect and interpret the data. The network used for communication included multiple ground stations positioned in different parts of the world so that continuous contact could be maintained as Earth rotated. This system allowed mission controllers to send commands and receive scientific data without interruption during critical phases of the mission. As the spacecraft moved farther along its path, its instruments began collecting scientific data about the environment of space between planets. This region contained charged particles, magnetic fields, and dust particles that provided information about conditions outside planetary atmospheres. The measurements helped scientists understand the behavior of solar wind and its interaction with planetary magnetic fields. These observations were recorded and transmitted back to Earth in structured datasets that could be analyzed by researchers. The design of the spacecraft included systems for managing power, which was supplied through long-lasting energy sources capable of functioning in deep space conditions. The power system allowed the instruments and communication equipment to continue operating even when the spacecraft was far from the Sun. Energy management was carefully balanced so that scientific instruments could remain active while communication systems continued transmitting data back to Earth. The mission timeline included a planned sequence of planetary encounters. The first major target region was the environment around Jupiter, where the spacecraft was expected to gather detailed information about the planet's atmosphere, magnetic field, and surrounding space. Instruments were activated during the approach phase to capture images and measurements of atmospheric movement, radiation levels, and particle activity. The data collected during this phase provided important scientific material for understanding planetary behavior. After passing the region around Jupiter, the spacecraft continued its journey toward Saturn. During this phase, systems on board continued operating under long-term conditions, and the communication network maintained regular contact with Earth. The spacecraft's instruments remained active, recording information about changes in space conditions as it moved through different regions of the solar system. The data transmission process continued through carefully scheduled communication sessions, allowing scientists to receive updates and adjust observation plans if needed. The spacecraft carried a collection of scientific instruments that included imaging devices, spectrometers, particle detectors, and magnetometers. Each instrument had a specific role in collecting different types of data. The imaging devices captured visual information about planetary surfaces and atmospheric patterns. Spectrometers analyzed light to determine the composition of gases and materials. Particle detectors measured the presence and movement of charged particles. Magnetometers recorded variations in magnetic fields across different regions of space. These instruments worked together to build a detailed understanding of the environments encountered during the mission. The engineering design of the spacecraft included protective structures that shielded its internal systems from radiation and temperature variations in space. These protective measures allowed the instruments to continue functioning during long periods of exposure to space conditions. The spacecraft was built to operate autonomously for extended periods, with onboard systems capable of managing routine operations without constant intervention from Earth. As the mission continued, the spacecraft passed through regions where the influence of the Sun's activity could still be measured. These measurements provided information about the extent of solar influence in space. The instruments recorded variations in particle density and energy levels, helping scientists understand how solar activity extends through the solar system. This data was transmitted back to Earth and processed by scientific teams working with mission control. The launch period in 1977 represented a stage in space exploration where robotic missions were designed to travel beyond previously explored regions. The development of this mission involved collaboration between engineers, scientists, and mission planners who worked together to create a system capable of long-distance operation. The spacecraft's design reflected careful attention to durability, communication ability, and scientific capability, ensuring that it could continue operating for extended periods while sending valuable information back to Earth. The spacecraft's journey included continuous monitoring by mission control teams, who tracked its position, system health, and data output. These teams analyzed incoming information and ensured that communication systems remained stable. Adjustments were made when necessary through command sequences sent from Earth. These commands allowed engineers to manage instrument settings, data collection schedules, and system performance. The scientific goals of the mission focused on collecting detailed information about planetary systems and the space environment beyond Earth. The data gathered included visual images, spectral readings, and particle measurements that contributed to a broader understanding of the solar system. The spacecraft's ability to operate across long distances allowed continuous observation over extended periods of time, providing a steady flow of information to researchers. The spacecraft continued its journey beyond the initial planetary regions, entering areas of space where fewer objects were present and where conditions were influenced by the outer boundaries of the solar system environment. Instruments remained active, recording variations in particle density, magnetic fields, and radiation levels. Communication signals continued to be received by Earth-based stations, allowing data to be collected and analyzed in ongoing research activities. The mission design included redundancy systems that allowed the spacecraft to continue operating even if certain components experienced reduced performance. These systems ensured that essential functions such as communication and data collection could continue under varying conditions. The spacecraft's onboard computer systems managed these operations through programmed instructions that guided its activities over long periods. The development and launch of Voyager 1 during the year 1977 reflected a period of active scientific expansion led by NASA, where exploration of distant planetary regions became a focus of research and technological advancement. The systems developed for this mission allowed continuous data collection, transmission, and analysis across distances that had not been previously explored by robotic spacecraft at that time. The spacecraft's structure included a large antenna used for communication with Earth. This antenna was designed to transmit and receive signals in deep space conditions. The signals carried scientific data, engineering information, and system status updates. These transmissions were decoded by ground stations and processed by computer systems for scientific interpretation. The instruments onboard the spacecraft were activated in stages after launch, allowing engineers to confirm that each system was functioning correctly. Calibration processes were performed to ensure that measurements were accurate. These calibrations were important for maintaining the reliability of scientific data collected during planetary observations. As the spacecraft moved through space, it encountered different regions with varying levels of particle activity and magnetic influence. The instruments recorded these variations continuously, allowing scientists to build a detailed record of space conditions along the spacecraft's path. The data collected contributed to understanding the structure of space beyond Earth's immediate environment. The mission required coordination between multiple teams responsible for spacecraft operation, scientific analysis, and communication management. These teams worked together to ensure that data collection remained consistent and that the spacecraft continued operating according to its planned objectives. The flow of information between Earth and the spacecraft remained active through scheduled communication sessions and automated data transmission processes. The systems on board the spacecraft were designed to operate under conditions of extreme distance from Earth, where communication delays became significant due to the time required for signals to travel. Despite these delays, the spacecraft continued sending data that was received and processed by ground stations, allowing scientists to maintain awareness of its condition and scientific output. The early phase of the mission set the foundation for long-term exploration of the outer solar system, with the spacecraft continuing to function as it moved through successive regions of space. The instruments remained active, the communication system remained operational, and the data flow continued as the spacecraft progressed along its planned trajectory through space beyond Earth's immediate environment. After the launch of Voyager 1, it slowly moved away from Earth, leaving behind the region where Earth's gravity is strongest and entering a path that would take it toward the outer parts of the solar system. In the early part of its journey, the spacecraft passed through space near Earth and then moved closer to the orbit of Mars. During this time, it remained active and stable, with its systems checked by mission control on Earth. Engineers monitored its signals, confirmed its instruments were working, and prepared it for its first major planetary encounter. The spacecraft continued to send weak but clear radio signals across space, and these signals were received by large antenna systems on Earth that were designed for deep space communication. As the spacecraft moved farther from the inner planets, it entered a region where sunlight was still present but weaker due to distance. It continued on a path that would bring it close to Jupiter. In the year 1979, it reached the Jupiter system and began its first major scientific study of a giant planet. At this stage, it collected detailed data using its cameras and sensors. It captured images of cloud movements in Jupiter's atmosphere, recording patterns that showed constant motion and changing structures in the upper layers of the planet's gases. The spacecraft also measured radiation around Jupiter. This region contains strong energy particles trapped by the planet's magnetic field. Instruments on board recorded how these particles moved and how intense the radiation environment was at different distances from the planet. These measurements were sent back to Earth in radio signals. Each signal traveled for a long time before reaching Earth, where scientists received and processed the information. During its time near Jupiter, the spacecraft also studied several of the planet's moons. It collected images of their surfaces and recorded data about their physical conditions. Some moons showed icy surfaces with visible cracks and patterns, while others showed rough terrain with many impact marks. The spacecraft gathered temperature readings and surface data, building a detailed record of these moons for the first time in close observation. The gravity of Jupiter also played an important role in the spacecraft's movement. As it passed near the planet, its path changed and its speed increased. This change allowed it to continue its journey deeper into the solar system without needing additional propulsion. After completing its observations, it left the Jupiter system and continued traveling outward. After leaving Jupiter, the spacecraft moved toward the outer regions of the solar system where Saturn is located. During the years 1980 and 1981, it approached Saturn and began another major phase of scientific study. Saturn appeared with a wide system of rings made of ice and dust particles. The spacecraft captured detailed images of these rings, showing their structure and the way particles were distributed in different layers. The instruments on board measured the environment around Saturn, including magnetic fields and charged particles. The spacecraft also studied Saturn's atmosphere, collecting information about its composition and movement. It recorded temperature readings and observed how different layers of gas behaved at various heights above the planet's surface. Saturn's moons were also part of the study. The spacecraft passed near several of them and collected data on their surfaces. It recorded differences in texture, brightness, and composition. Some moons showed smooth, icy areas, while others had rough and heavily marked surfaces. The spacecraft continued sending this information back to Earth in a steady flow of data transmissions. One of the important effects of Saturn's gravity was the way it changed the spacecraft's direction. This gravitational interaction adjusted its path so that it could continue moving outward from the solar system. After completing its observations, the spacecraft left the Saturn region and began traveling into deep space beyond the main planetary zones. As the spacecraft moved away from Saturn, it entered a region where the Sun still had an influence, but that influence gradually became weaker with distance. This region contains solar wind, which is a continuous flow of charged particles released from the Sun. The spacecraft carried instruments that measured this solar wind, recording its speed, density, and direction. It also measured magnetic fields carried by the solar wind, helping scientists understand how space behaves far from the Sun. During this long journey outward, the spacecraft remained in contact with Earth through deep space communication networks. These networks use large radio antennas placed in different parts of the world. The signals sent by the spacecraft became weaker as distance increased, but they were still received and decoded. Each transmission carried information about the spacecraft's systems and scientific measurements. As time passed, the spacecraft entered a region of space where the influence of the Sun began to weaken further. The environment became less dominated by solar particles and more influenced by particles from other parts of the galaxy. The spacecraft continued to measure these changes using its instruments, recording variations in particle types and energy levels. In the year 2012, the spacecraft reached a major boundary region known as the heliopause. This is the outer edge of the Sun's influence, where solar wind slows down and interstellar space begins. At this point, the spacecraft recorded changes in particle direction and intensity. It measured a reduction in solar particles and an increase in particles coming from interstellar space. These measurements were sent back to Earth, where scientists studied the transition in detail. When the spacecraft crossed into interstellar space in the year 2012, it continued to operate with reduced power. Its energy source slowly weakened over time, but essential systems remained active. Instruments that measured particles, fields, and radiation continued to function. Some systems were turned off to save energy, while others remained active to support the main scientific mission. Communication between the spacecraft and Earth became slower due to the increasing distance. Radio signals took many hours to travel across space before reaching Earth. Despite this delay, communication remained steady. Mission Control continued to send commands, and the spacecraft continued to respond when possible. In interstellar space, the spacecraft measured particles that were not shaped mainly by the Sun. It recorded cosmic radiation, which consists of high-energy particles moving through space from distant sources. It also measured magnetic fields in this region, providing information about the environment between star systems. The spacecraft detected changes in the density of particles as it moved farther away from the heliopause. These changes were recorded continuously and sent back to Earth. Scientists used this information to study how interstellar space behaves and how it differs from regions closer to the Sun. As the spacecraft moved deeper into interstellar space, its power system continued to decline slowly. The onboard systems were carefully managed to extend the mission. Only the most important instruments were kept active, while others were shut down permanently. This allowed the spacecraft to continue sending scientific data for as long as possible. The spacecraft also continued to measure magnetic fields in interstellar space. These fields showed variations over time, and the spacecraft recorded these changes with precision. It also measured cosmic rays, which are high-energy particles that travel through space at high speeds. These measurements helped build a long-term record of conditions far beyond the solar system. The signals sent by the spacecraft continued to travel across vast distances before reaching Earth. Each signal carried information about the spacecraft's position, condition, and scientific observations. Large antenna systems on Earth received these signals and converted them into data that scientists could study. As the spacecraft continued its outward movement, it entered regions where solar influence was extremely weak. The environment was dominated by interstellar particles, and the spacecraft recorded detailed measurements of these conditions. It continued to detect changes in particle direction, energy levels, and density. The spacecraft's instruments remained stable, even as available power decreased. Engineers on Earth carefully managed the remaining energy by turning off systems that were not essential. This allowed the spacecraft to continue its core scientific functions. In this distant region of space, the spacecraft continued to gather information about radiation and particle movement. It recorded how particles interacted with magnetic fields and how energy was distributed in interstellar space. These observations were sent back to Earth over long communication delays. The spacecraft's path remained steady as it moved farther away from the Sun. It continued to transmit data at regular intervals, and each transmission provided updated information about its condition. Scientists monitored these signals carefully to ensure that the spacecraft remained operational. The environment around the spacecraft continued to show low particle density and weak magnetic fields. These conditions were recorded continuously and sent back to Earth for analysis. The data provided a long-term view of the outer regions of space. The spacecraft also measured cosmic radiation levels, which remained an important part of its scientific mission. These measurements helped scientists understand how high-energy particles move through interstellar space and how they interact with magnetic fields. As the spacecraft continued its journey, it remained one of the most distant active objects made by humans. It kept moving outward, carrying instruments that still functioned in a limited but steady way. Communication continued through deep space networks, and scientific data continued to be collected. The spacecraft systems were designed to operate for long periods, and even with reduced energy, it continued to perform key measurements. It recorded particle flows, magnetic field changes, and radiation levels in interstellar space. As it moved farther away, the signals it sent became even weaker, but they still reached Earth. Each signal carried valuable information that was carefully processed and stored. Scientists continued to track the spacecraft's progress and study the data it provided. The spacecraft continued to travel through interstellar space, where conditions are shaped by particles from distant sources rather than solar activity. It recorded these conditions steadily, adding to a long record of observations from beyond the solar system. As Voyager 1 moved farther away, it entered regions where the solar wind, which is a continuous flow of charged particles from the Sun, began to weaken. This region is part of the structure known as the heliosphere. The heliosphere is formed by the Sun's constant release of particles and magnetic fields that expand outward in all directions. This outward flow creates a large region of space that is filled mainly with solar material. The outer edge of this region is not a solid boundary, but a zone where the solar wind becomes slower, more compressed, and gradually less dominant. Beyond this region lies interstellar space, where the influence of the Sun becomes weaker and the environment is shaped more by material from other stars. Voyager 1 continued its journey through this changing environment for many years after leaving the planetary region. Its instruments measured variations in particle density and changes in magnetic fields as it moved outward. These measurements showed that the environment was not uniform but changed gradually over large distances. The spacecraft recorded data about charged particles, including protons and electrons, which are influenced by solar activity and by cosmic radiation from outside the solar system. The instruments also recorded the direction and strength of magnetic fields, which helped scientists understand how the heliosphere is structured in its outer regions. As time passed, Voyager 1 reached a region where the solar wind slowed down significantly. This region is known as the termination shock. In this area, the outward flow of particles from the Sun becomes slower because it begins to interact more strongly with particles in interstellar space. The spacecraft passed through this region after many years of travel, and its instruments recorded changes in particle energy and density. The data showed that the environment became more complex, with increased turbulence and variations in charged particle behavior. After passing the termination shock, Voyager 1 entered a region called the Helios Heath. This is a thick outer layer of the heliosphere where the solar wind is slowed and compressed but still present. The Helios sheath contains particles that have been influenced by both the Sun and the interstellar environment. In this region, the spacecraft continued to collect information about cosmic rays, magnetic fields, and plasma waves. The density of particles increased compared to earlier regions, and the behavior of the solar wind became more irregular. The instruments on Voyager 1 continued to operate and send data back to Earth through very weak radio signals due to the great distance. The journey through the Helios sheath took many years. During this time, scientists observed gradual changes in the data received from the spacecraft. The number of low-energy charged particles decreased, while higher energy particles from outside the solar system became more prominent. These changes indicated that Voyager 1 was approaching the outer boundary of the heliosphere. The spacecraft's position was tracked carefully using radio signals, and its distance from the Sun continued to increase steadily. At a later stage, Voyager 1 approached a region where the solar wind becomes extremely weak and begins to blend with interstellar material. This region is known as the heliopause. The heliopause is not a sharp physical wall, but a boundary zone where the pressure of the solar wind balances with the pressure of interstellar space. At this location, the influence of the Sun's particles becomes very small, and particles from outside the solar system become more dominant. The spacecraft's instruments detected changes in particle composition, including a decrease in solar origin particles and an increase in galactic cosmic rays. In the year 2012, Voyager 1 reached a major change in its environment. The data showed that the spacecraft had entered a region where solar particles were greatly reduced and where cosmic rays from interstellar space were significantly higher. The magnetic field measurements also showed alignment with the broader interstellar magnetic field. This indicated that the spacecraft had moved beyond the main influence of the solar wind. the plasma wave instrument detected vibrations caused by plasma in interstellar space, which provided additional confirmation of the surrounding environment. Even after this transition, Voyager 1 continued to send data back to Earth. The communication required a very large and sensitive network of antennas known as the Deep Space Network, which receives weak signals from distant spacecraft. The signals take many hours to travel between the spacecraft and Earth due to the vast distance. Engineers carefully monitor the strength and quality of the signals to ensure that information continues to be received. As Voyager 1 moved farther into interstellar space, the density of charged particles around it became more stable compared to the changing conditions inside the heliosphere. The spacecraft measured cosmic rays originating from distant stars and from energetic processes in the galaxy. These particles are different from those produced by the Sun, and their presence helped confirm that Voyager 1 had moved into a region dominated by interstellar material. The magnetic field data collected by Voyager 1 also showed a steady direction and strength consistent with interstellar space. Before crossing the heliopause, the magnetic field in the heliosheath showed variations influenced by solar activity. After crossing into interstellar space, the magnetic field became more consistent, indicating a different environmental structure. During the transition period, the plasma wave instrument played an important role. It detected oscillations in the surrounding plasma that allowed scientists to estimate the density of the material around the spacecraft. These measurements showed a clear increase in plasma density after the spacecraft entered interstellar space. This change provided strong evidence that Voyager 1 had left the heliosphere and entered a new region of space. The spacecraft's power source is a radioisotope thermoelectric generator, which produces electricity from the heat of decaying material. Over time, the power output slowly decreases, and mission controllers manage the available energy carefully by turning off non-essential instruments. This allows critical systems, such as communication and essential scientific instruments, to continue operating for as long as possible. Even with reduced power, Voyager 1 continues to perform measurements that provide valuable information about interstellar conditions. The position of Voyager 1 is tracked using radio signals that travel at the speed of light. Because of the distance, there is a long delay between sending a command from Earth and receiving a response from the spacecraft. This delay increases as the spacecraft moves farther away. Despite this, communication remains possible, and data continues to be transmitted in small amounts due to limited power and antenna strength. As Voyager 1 moved deeper into interstellar space after its boundary crossing, the environment around it showed more stable conditions in particle density and magnetic field structure. The spacecraft recorded fewer variations caused by solar activity and more consistent readings influenced by the broader galactic environment. The instruments continued to measure cosmic rays, plasma waves, and magnetic field direction, contributing to an understanding of how space behaves beyond the influence of the Sun. The heliosphere itself is shaped by the balance between outward solar wind pressure and inward pressure from interstellar space. This balance creates layers within the heliosphere, including the termination shock, heliosheath, and heliopause. Voyager 1 passed through each of these regions over a long period of time, with each transition marked by changes in the data collected by its instruments. The gradual movement through these layers provided direct measurements of conditions that could not be observed from Earth alone. The crossing into interstellar space marked a change in the type of particles that dominated the environment around the spacecraft. Inside the heliosphere, most particles originate from the Sun, while outside, particles come from distant stars and cosmic events. Voyager 1's instruments recorded this shift in particle sources, showing a reduction in solar wind particles and an increase in galactic cosmic rays. The spacecraft's journey beyond the heliosphere also provided continuous information about the shape and extent of the Sun's influence in space. The heliosphere extends far beyond the orbit of Pluto, and its outer boundary varies depending on solar activity and interstellar conditions. Voyager 1's measurements helped refine the understanding of this structure by providing direct data from within it and beyond it. The data collected after the boundary crossing includes measurements of plasma density, magnetic field orientation, and cosmic ray intensity. These measurements help describe the environment of interstellar space near the solar system. The region is filled with sparse plasma and energetic particles that move through space over long distances. Voyager 1 continues to sample these conditions as it travels farther away. The spacecraft's instruments operate in a very low energy environment, and their performance is adjusted to match the available power. Some instruments have been turned off to conserve energy, while others continue to function in reduced modes. Despite these limitations, Voyager 1 still provides valuable scientific information. The communication system relies on a large antenna on Earth that receives weak signals from deep space. The signal strength decreases as the distance increases, requiring precise calibration and monitoring. The data received is stored and analyzed to study long-term changes in interstellar space conditions. The environment beyond the heliosphere is influenced by material from other stars in the galaxy. This material includes charged particles, magnetic fields, and radiation that travel through space over long periods. Voyager 1's measurements provide direct information about these conditions in a region that had not been directly sampled before. The Voyager 1, along with its scientific instruments, also carries a special physical object known as Voyager Golden Record. This record was created as a message intended for any possible civilization that might encounter the spacecraft in the distant future. It was designed as a collection of sounds, images, and information meant to describe Earth, life on Earth, and the position of humanity within the wider environment of space. The idea behind the Golden Record began with a group of scientists, engineers, and thinkers who worked with the space mission team. They wanted to prepare a message that could be placed on a spacecraft that would travel far beyond the region of planets and continue moving through space for very long periods. The spacecraft itself would carry instruments for scientific study, but the record would carry information meant for communication beyond Earth. This record was made in the form of a phonograph disc covered in gold plating to help protect it from damage caused by particles, radiation, and time in space. The surface of the record contains carefully arranged information that can be read if a suitable technology is used to play it. The content of the Golden Record includes many different types of recorded material. It contains sounds from Earth, spoken greetings in many languages, music from different cultures, and a collection of images encoded in a way that can be reconstructed. Each part of the record was selected with the intention of giving a wide view of human life and natural life on Earth. The sounds included are natural and human-made sounds. Natural sounds include wind, rain, thunder, ocean waves, and animal sounds. Human-made sounds include tools, machines, and everyday activities that represent daily life. The spoken greetings included on the record are recorded in many languages from different regions of the world. Each greeting is a short message that welcomes the listener and identifies the intention of peaceful communication. These greetings were selected to show the presence of many languages spoken by people across different regions. The recording process involved speakers of each language carefully pronouncing the chosen phrases so that the message could be preserved clearly on the record. The languages were selected to represent a wide range of human communication styles and cultural backgrounds. The musical selections included on the Golden Record cover a wide range of musical traditions. These pieces include instrumental compositions and vocal performances. The music was chosen to reflect different ways humans express ideas and emotions through sound. The selection includes music that uses different instruments, rhythms, and structures. Each piece was recorded with care so that the sound quality would remain stable when played in the future using the correct method. The images included on the record are stored in a form that can be reconstructed by decoding the signals recorded on the disc. These images include representations of human beings, human activities, natural environments, scientific diagrams, and everyday objects. The images show food preparation, medical processes, buildings, transportation systems, and family life. They also include images of animals, plants, and landscapes from Earth. Each image was chosen to provide visual information about life and the environment of the planet where the spacecraft originated. The Golden Record also includes instructions on how to play the disc. These instructions are encoded using symbolic diagrams that show how to construct a playback system using basic scientific principles. The instructions include information about the correct speed of rotation, the position of the stylus, and how to convert recorded signals into sound and images. These instructions are meant to allow someone with advanced understanding of physics and engineering to interpret the message even if they are unfamiliar with human technology. The physical structure of the record is made from copper covered in gold plating. Gold was chosen because it resists corrosion and can survive long exposure to space conditions. The record is stored in a protective aluminum cover attached to the spacecraft. The cover also includes diagrams that show the location of Earth in relation to known astronomical objects. These diagrams are based on pulsar locations and mathematical descriptions of their positions. The purpose of these diagrams is to provide a reference system that could help identify the origin of the spacecraft. The spacecraft Voyager 1 continues its journey beyond the region of planets, carrying the Golden Record further into space. The record is not expected to be used in any human mission after launch. Instead, it remains attached to the spacecraft as it moves through regions where human presence does not exist. The information on the record remains unchanged since its creation, preserving a fixed snapshot of human life at the time of its preparation. The selection of sounds included on the record involved careful decision-making by the team responsible for its creation. Natural sounds were selected to represent environmental conditions found in many parts of Earth. The sound of rain was included to represent weather patterns that occur in many regions. Thunder was included as an example of atmospheric electrical activity. Ocean waves were included to represent large bodies of water in motion. Bird calls and animal sounds were included to represent living organisms in natural environments. Human-made sounds included footsteps, heartbeats, laughter, and speech in different settings. These sounds were chosen to represent physical human presence and daily activity. Mechanical sounds included tools and machines used in various tasks. These recordings were made in controlled environments to ensure clarity and consistency. Each sound was recorded using equipment that captured a wide range of frequencies so that the details could be preserved. The musical part of the Golden Record includes compositions from different regions of Earth. These include solo performances, orchestral arrangements, and traditional music using instruments that produce sound through strings, airflow, percussion, and electronic methods. Each selection was chosen to represent a different form of musical expression. The recordings were made with high-quality audio systems to preserve tonal detail and structure. The spoken greetings included on the record are arranged in a sequence. Each greeting is spoken once in its original language. The phrases generally express goodwill and peaceful intent. The recording includes voices from different age groups and cultural backgrounds. The pronunciation was carefully practiced before recording to ensure clarity. The final recorded greetings were tested to confirm that they could be reproduced clearly when decoded. The image collection stored on the golden record includes structured information that allows reconstruction of each picture. The images are encoded in binary form and arranged in a sequence. They include diagrams of human anatomy showing skeletal structure and internal organs. They include representations of Earth's position in the solar system. They include illustrations of scientific concepts such as chemical structures and physical processes. The images also include representations of daily human activities such as cooking, writing, and social interaction. The preparation of the golden record required coordination between scientists, engineers, artists, linguists, and cultural representatives. Each group contributed to the selection of content. The process involved reviewing possible materials and deciding which ones would best represent the variety of life and knowledge on Earth. The final collection was transferred onto the physical disc using precise recording techniques. The protective cover of the record includes etched diagrams that show how to interpret the information. One diagram shows the hydrogen atom transition, which is used as a universal reference for time and length. Another diagram shows how the record should be rotated and how the sound is stored along the grooves. These diagrams were designed to be understood through logical interpretation of physical patterns. The spacecraft Voyager 1 carries this record as it moves further away from the solar region where Earth is located. The record remains fixed to the spacecraft and does not change over time. The materials used in its construction were selected for durability under conditions of radiation, vacuum, and temperature variation. The record continues to function as a stored collection of information rather than an active communication device. The sounds of Earth included on the golden record extend beyond natural and human environments. They include sounds from different regions of daily life, such as markets, transportation systems, and work environments. These sounds were recorded in different locations and combined into a structured archive. Each sound was selected to represent common activities that occur in human societies. The recording process involved placing microphones in controlled positions to capture clear audio without distortion. The music selection process included evaluation of rhythm, tone, cultural origin, and instrumentation. The selected pieces include works from multiple continents and time periods. Each piece was recorded in a format suitable for long-term storage. The goal was to preserve the original sound characteristics without alteration. The recordings were tested for clarity and consistency across playback systems. The images on the record include step-by-step sequences showing human movement and interaction. They include visual representations of gestures, tools in use, and environmental surroundings. The encoding process involved converting visual data into numerical form. This allowed the images to be stored in a compact format that could be reconstructed when decoded correctly. The Golden Record also includes scientific diagrams that show physical principles such as atomic structure and mathematical relationships. These diagrams were designed to communicate basic scientific knowledge in a structured format. They include references to time measurement based on atomic transitions and spatial measurement based on universal constants. The preparation of the record involved decisions about what types of information would be most appropriate for long-term storage in space. The content reflects a wide range of human experience at the time of its creation. The inclusion of language, sound, and image provides multiple ways of representing information. Each type of content is stored in a format that can be interpreted through logical decoding. The spacecraft Voyager 1 continues its movement through regions beyond the influence of the Sun's immediate environment. The Golden Record remains attached to the spacecraft as part of its structure. The record continues to carry encoded information about Earth's environment, human communication, and cultural expression. The materials used in the record's construction were chosen to remain stable under long exposure to space conditions without degradation that would prevent reading of the stored information. The Golden Record includes structured sequences of data that represent both sound and image. The sound grooves contain analog signals that represent vibrations corresponding to recorded audio. The image data is arranged in patterns that correspond to brightness and contrast levels. These patterns can be decoded into visual representations when processed using the correct method. The overall structure of the record reflects a systematic arrangement of information. Each section of the record is designed to represent a different category of content. The arrangement allows for reconstruction of the full set of materials when properly interpreted. The physical format ensures that the record can be played using mechanical reproduction methods. The inclusion of the Golden Record on Voyager 1 ensures that the spacecraft carries a preserved collection of Earth-based information into regions of space far beyond planetary boundaries. The record continues to exist as a fixed archive of sounds, images, and messages prepared during the mission design phase. The information stored on the record remains unchanged as the spacecraft continues its movement through distant space regions without interruption. The work of NASA in monitoring Voyager 1 is a continuous scientific and engineering activity that has continued for many decades without interruption. It involves constant attention to weak signals, careful planning of communication schedules, detailed interpretation of data, and ongoing adjustments to systems that were originally designed for a much shorter mission duration. As it moved farther, the challenge of communication increased steadily, and the responsibility of tracking it remained with NASA and its network of ground systems that support deep space communication. The monitoring process begins with the transmission of signals from Earth toward the spacecraft. These signals are sent using large antennas that are part of a global communication system managed by NASA. The signals travel through space at the speed of light and take many hours to reach Voyager 1 because of its extreme distance from Earth. The spacecraft receives these signals using its onboard antenna, which is pointed toward Earth with careful alignment. This alignment is necessary because the signal strength becomes weaker as distance increases, and even small changes in direction can affect whether the spacecraft receives instructions correctly. The commands sent from Earth include instructions for scientific instruments, communication settings, and adjustments to how the spacecraft operates its systems. After receiving commands, Voyager 1 processes them using its onboard computer system. This system was built with technology from the time of its launch, and it continues to function in a stable but limited way. The commands are stored and then carried out step by step. Some commands control scientific instruments that measure particles, magnetic fields, and radiation in space. Other commands control the orientation of the spacecraft so that its antenna remains directed toward Earth. The accuracy of this orientation is very important for communication, since the signal beam is narrow and must remain aligned with Earth's receiving antennas managed by NASA. Once the spacecraft completes its tasks, it sends data back toward Earth. This data includes scientific measurements as well as information about the health of the spacecraft. The transmission from Voyager 1 is extremely weak by the time it leaves the spacecraft, and it becomes even weaker as it travels across the vast distance of space. When the signal reaches Earth, it is many times weaker than the natural background noise of space. Because of this, NASA uses highly sensitive receiving antennas that are designed to collect and strengthen the signal enough for interpretation. These antennas are part of a coordinated system that operates in different locations on Earth so that communication can continue as the planet rotates. The signals received from Voyager 1 are not immediately readable in their raw form. They must be processed using specialized computers and software. These systems remove noise, identify patterns in the signal, and reconstruct the data into meaningful information. The data is then analyzed by teams of scientists and engineers working with NASA. They study the results to understand the conditions in interstellar space, the environment surrounding the spacecraft, and the performance of the spacecraft systems. The tracking of Voyager 1 involves determining its exact position in space at any given time. This is done using radio signals that allow scientists to measure the time it takes for a signal to travel between Earth and the spacecraft. Because the speed of light is constant, the delay in communication can be used to calculate distance. As the spacecraft moves farther away, this delay becomes longer. NASA uses this information to update models of the spacecraft's trajectory, ensuring that communication antennas remain pointed in the correct direction. The communication system that supports this work is designed to handle extremely long distances. It relies on powerful transmitters on Earth and large receiving dishes that can detect faint signals. These systems must remain operational at all times because even short interruptions could result in missing important data. The coordination of these systems is managed by NASA through scheduled communication windows. During these windows, commands are sent, and data is received from Voyager 1. Each communication session is carefully planned based on the spacecraft's position and the availability of ground stations. Over time, the strength of the signal from Voyager 1 has decreased due to its increasing distance from Earth. To address this, NASA has made adjustments to both the spacecraft and the ground systems. On the spacecraft side, some instruments have been turned off to conserve power, allowing the remaining systems to continue operating. The spacecraft's power source, which is based on radioisotope energy, gradually produces less energy as time passes, so careful management of power consumption is necessary. On the ground, improvements in signal processing techniques have been made to enhance the ability to detect and interpret weak transmissions. The process of communicating with Voyager 1 also involves handling delays that grow longer as the spacecraft moves farther away. A signal sent from Earth takes many hours to reach the spacecraft, and a response takes the same amount of time to return. This means that a single exchange of information can take an entire day or more to complete. Because of this delay, operations must be planned in advance. NASA prepares sequences of commands that the spacecraft can execute without immediate feedback. These sequences are carefully tested before being sent to ensure that they will not cause problems during execution. The communication system must also account for the rotation of Earth. Since ground antennas cannot always point toward Voyager 1 at all times, different stations take turns receiving and transmitting signals. This ensures continuous coverage over long periods. NASA coordinates these stations so that there are no gaps in communication during critical operations. Each station plays a role in maintaining the link between Earth and the spacecraft, and their operation is synchronized with the spacecraft's expected signal arrival times. Another important part of monitoring involves checking the health of Voyager 1. The spacecraft regularly sends telemetry data, which includes information about temperature, power levels, instrument status, and system performance. Engineers at NASA analyze this data to detect any signs of malfunction or degradation. If a problem is detected, they attempt to correct it by sending new commands. These corrections must be carefully designed because the spacecraft operates in a distant environment where immediate testing is not possible. There have been situations where communication with Voyager 1 has experienced interruptions or unusual data patterns. In such cases, NASA engineers work to identify the cause of the issue by examining both the spacecraft systems and the communication chain. They consider possible causes such as software errors, hardware aging, or signal distortion during transmission. Once the cause is identified, corrective commands are developed and transmitted during the next communication window. The process of maintaining communication also depends on predicting the future path of Voyager 1. Although the spacecraft is traveling in a mostly steady direction, small gravitational influences and other factors are considered in its trajectory models. NASA uses these models to adjust antenna pointing directions on Earth so that the spacecraft remains within the receiving range. These predictions are updated regularly based on new tracking data. As the spacecraft continues its journey, the role of power management becomes increasingly important. The energy source on Voyager 1 slowly decreases over time, which requires careful selection of which systems remain active. NASA decides which instruments are still necessary for scientific objectives and which can be turned off to preserve energy. This balancing process allows the spacecraft to continue transmitting data for as long as possible. The communication system also involves maintaining software integrity on Voyager 1. The spacecraft's onboard software controls nearly all of its operations. Updates or changes to this software must be transmitted carefully, as errors could disrupt communication or scientific functions. NASA prepares these updates in a structured format and sends them in segments due to the limited bandwidth of the communication channel. The data received from Voyager 1 is used not only for monitoring the spacecraft itself, but also for studying the environment beyond the influence of the Sun's solar wind. This environment provides valuable information about interstellar space. Scientists working with NASA analyze changes in particle density, magnetic field direction, and radiation levels to understand conditions far from the solar system. The communication link between Earth and Voyager 1 remains one of the most distant and long-running connections between a human-made object and Earth. Maintaining this link requires continuous effort from NASA engineers, scientists, and support teams. Each message sent and received is part of a structured system designed to ensure that the spacecraft remains operational and that its scientific mission continues without interruption. The antennas on Earth used by NASA are designed to capture extremely weak signals. These antennas must remain highly accurate in their pointing direction. Even very small misalignments can reduce the quality of the received signal. To To prevent this, calibration procedures are performed regularly. These procedures involve adjusting the antenna systems based on known reference points and updated spacecraft position data. The monitoring of Voyager 1 also includes long-term planning. Because communication delays increase as distance grows, the system must anticipate future needs well in advance. NASA prepares command schedules that may cover extended periods of spacecraft activity. These schedules ensure that the spacecraft continues to operate even when direct real-time control is not possible. The scientific value of the data returned by Voyager 1 depends on the ability of NASA to maintain consistent communication. Even small amounts of data are carefully preserved and studied. Each dataset contributes to a growing record of conditions in deep space. This record helps scientists understand how space changes with distance from the Sun and how cosmic particles behave in regions beyond the solar system boundary. The system used by NASA to communicate with Voyager 1 continues to adapt as conditions change. Improvements in signal processing, data compression, and antenna technology allow the spacecraft to remain in contact despite increasing distance. These improvements are applied carefully to avoid disrupting the existing communication structure. The monitoring process remains active at all times, with continuous observation of signal strength, data quality, and spacecraft status. Every piece of information received from Voyager 1 is processed and reviewed. The work of NASA in this context involves sustained attention to detail, long-term planning, and precise coordination between Earth-based systems and the distant spacecraft, allowing communication to continue across the expanding distance of space. Far away from Earth, beyond the outer planets, and moving steadily into deep space, the spacecraft known as Voyager 1 continued its long journey after completing its main mission of studying the giant planets. It had already passed by Jupiter and Saturn, sending back detailed information about their atmospheres, moons, and magnetic fields. After this phase of exploration was completed, it did not stop or turn around. Instead, it kept moving farther and farther away, carried forward by the speed it had gained during its planetary encounters. Its path was carefully planned so that it would leave the plane of the solar system and travel into regions that had never been visited by any human-made object. As it moved farther from the Sun, the brightness of sunlight began to decrease slowly. The planets became distant points, and the region that had once been filled with familiar objects started to thin out. The spacecraft entered a part of space where there were fewer particles, less radiation from the Sun, and a much weaker influence of the solar wind. During this time, scientists working at NASA were still closely monitoring the spacecraft. They continued to receive signals, though these signals took longer and longer to reach Earth due to the increasing distance. At a certain point during this long journey, a remarkable idea was suggested by the astronomer Carl Sagan. He believed that before the spacecraft went too far into deep space, it should turn its camera back toward the inner solar system and take a final set of images. This idea was not part of the original mission plan, and it required careful consideration. The cameras on the spacecraft were not designed to operate indefinitely, and there was concern about pointing them toward the Sun, which could damage the sensitive instruments. Despite these concerns, the idea was eventually approved after discussions and planning. By this time, Voyager 1 was already at an enormous distance from Earth. It had traveled billions of miles away, far beyond the orbit of Neptune. The sunlight in that region was much weaker than it is near Earth, and capturing images would be more difficult. The spacecraft needed to be carefully oriented so that its cameras could take pictures of the planets without being overwhelmed by the brightness of the sun. Engineers calculated the angles and timing required for this maneuver, ensuring that the instruments would not be exposed to harmful levels of light. In the year 1990, the spacecraft executed this special command. It slowly rotated its body, adjusting its orientation so that its camera system, known as the Imaging Science Subsystem, could look back toward the Sun and the inner solar system. This movement was not rapid. It had to be done with precision, using small thrusters that adjusted the spacecraft's position. Every movement was controlled from Earth, with commands sent across a vast distance, taking many hours to arrive. Once the spacecraft was in the correct position, it began to take a series of images. These images were not just of Earth. They included several of the planets, captured from a perspective that had never been seen before. The collection of images later became known as the family portrait of the solar system. Each planet appeared as a small point of light against the darkness of space. The images were faint and required careful processing to be clearly visible. Among these images was one that would become especially well known. In this particular image, Earth appeared as an extremely small point of light. It was not large or detailed. It did not show continents or oceans in a clear way. Instead, it appeared as a tiny pale dot suspended in a beam of scattered sunlight. This beam was created by light reflecting within the camera system, forming a streak across the image. Within this streak, the small point representing Earth could be seen. At the time the image was taken, Voyager 1 was about 4 billion miles away from Earth. This distance was far greater than any distance from which a photograph of Earth had ever been captured. The signal carrying this image data had to travel across that immense distance before it could be received on Earth. The data was transmitted as radio signals, moving at the speed of light, yet still taking several hours to arrive. The process of receiving the image was not immediate. The signals were extremely weak by the time they reached Earth. Large radio antennas, such as those in the Deep Space Network operated by NASA, were used to detect and collect these signals. The data was then processed and assembled into images. Each image required time to reconstruct, as the information was sent in small pieces and had to be carefully combined. When the image of Earth was finally processed and viewed, it appeared very different from the images people were used to seeing. Unlike the detailed photographs taken by satellites orbiting Earth, this image showed Earth as a tiny speck. It occupied only a small fraction of a single pixel in the camera's field of view. The color was faint, giving it a pale appearance. The surrounding space was mostly dark, with faint streaks of light caused by the camera's optics. The significance of this image did not come from its clarity or detail, but from the perspective it provided. For the first time, Earth had been photographed from such a vast distance, showing how small it appeared in the larger environment of the solar system. The image captured the position of Earth relative to the Sun and the surrounding space, offering a view that had never been seen before. The decision to take this image marked the end of Voyager 1's imaging mission. After this set of photographs was completed, the spacecraft's cameras were turned off permanently. This was done to conserve power, as the spacecraft relied on a limited energy source generated by a radioisotope thermoelectric generator. The energy produced by this system decreased gradually over time, so it was necessary to prioritize which instruments would remain active. Even after the cameras were turned off, Voyager 1 continued to send back valuable data. It carried instruments designed to study cosmic rays, magnetic fields, and particles in space. These instruments continued to operate as the spacecraft moved farther away from the Sun, eventually reaching the boundary where the influence of the solar wind began to weaken significantly. The pale blue dot image became widely recognized after it was shared and discussed by Carl Sagan. He described the image in a way that emphasized the small size of Earth as seen from that distance. His explanation drew attention to the fact that everything known to humanity, including all people, history, and events, existed within that tiny point of light. His words helped many people understand the importance of the image and the perspective it provided. The technical challenges involved in capturing this image were significant. The camera system on Voyager 1 was designed to capture images of planets at relatively closer distances. Taking a photograph of Earth from billions of miles away required careful adjustments to exposure and timing. The brightness of the sun, even from that distance, posed a risk to the camera sensors. Engineers had to ensure that the camera was pointed in a way that minimized direct exposure to sunlight while still capturing the desired images. The spacecraft's ability to carry out this task depended on its precise navigation and control systems. These systems allowed it to maintain its orientation in space and execute commands sent from Earth. The communication delay meant that there was no immediate feedback during the maneuver. Engineers had to rely on calculations and predictions to ensure that the spacecraft would perform as expected. The data transmission process also required careful management. The bandwidth available for sending data from Voyager 1 was limited, and the signal strength decreased with distance. This meant that images had to be transmitted slowly, with each piece of data carefully encoded and sent over time. The receiving stations on Earth had to be sensitive enough to detect these weak signals and reconstruct the images accurately. The image itself shows a narrow beam of light, with Earth appearing as a small dot within it. The beam is caused by scattered sunlight within the camera system, creating a visual effect that was not part of the original scene, but resulted from the interaction of light with the instrument. Despite this effect, the position of Earth can be identified within the image, providing a clear indication of its location relative to the Sun. The distance at which the image was taken highlights the scale of the solar system. From that position, the planets appear as small points, and the vast space between them becomes more apparent. The image does not show the full extent of the solar system, but it provides a glimpse of how objects within it are distributed when viewed from a distant perspective. Voyager 1 continues to send data after many decades because it was designed with a deep level of care, planning, and attention to detail that allowed it to survive far longer than most machines ever built. Every part of the spacecraft was created with the expectation that it would travel into a region where no human-made object had ever gone before, far beyond the reach of repair, far beyond the ability to replace broken parts, and far beyond the safety of the environment close to Earth. This meant that from the very beginning, the engineers who built it had to imagine every possible problem that might occur over many years and prepare for those problems in advance. One of the most important reasons why Voyager 1 still sends data is its power system. The spacecraft does not use solar panels like many satellites near Earth. Solar panels depend on sunlight, and as a spacecraft travels farther away from the Sun, the sunlight becomes weaker. At the distance where Voyager 1 now travels, sunlight is far too weak to generate useful electrical power. Because of this, the engineers used a special type of power source known as a radioisotope thermoelectric generator. This device produces electricity by using heat from the natural decay of a radioactive material. Inside the generator, a material slowly breaks down over time, releasing heat. That heat is then converted into electricity using solid-state devices that have no moving parts. The absence of moving parts is very important because moving parts can wear out, break, or fail over time. By removing this risk, the generator can continue working steadily for many years. The radioactive material inside the generator does not stop producing heat quickly. It decays very slowly, which means it can provide power for decades. However, the amount of power it produces decreases gradually as time passes. The engineers knew this would happen, so they designed the spacecraft in such a way that it could operate even as its available power slowly dropped. Over the years, scientists on Earth have turned off certain instruments and systems that are no longer needed, so that the remaining power can be used to keep the most important parts running. This careful management of power has allowed Voyager 1 to continue functioning long after its original mission goals were completed. Another key reason for its long survival is the simplicity and strength of its design. The spacecraft was built to handle extreme conditions, including very low temperatures, high levels of radiation, and the vacuum of space. The materials used in its construction were chosen because they could withstand these conditions without breaking down quickly. The electronics were also built with a high level of reliability in mind. At the time of its construction, engineers used technologies that were well understood and tested, rather than choosing newer and less proven designs. This approach reduced the risk of unexpected failures. Voyager 1 also benefits from redundancy in some of its systems. Redundancy means that there are backup components that can take over if a primary component fails. For example, the spacecraft has multiple communication systems and multiple ways to control its orientation. If one system stops working, another can be used instead. This increases the chances that the spacecraft can continue operating even if some parts fail over time. The ability to switch between systems has been used many times during its journey to solve problems and keep the mission going. Communication is another major factor in why Voyager 1 still sends data. The spacecraft is equipped with a high-gain antenna, which is a large dish that focuses radio signals into a narrow beam. This allows it to send signals over extremely long distances. Even though the signals become very weak by the time they reach Earth, they can still be detected using large radio antennas on the ground. These antennas are part of a network that is designed to receive signals from distant spacecraft. The network uses very sensitive equipment to detect faint signals and extract information from them. The communication system on Voyager 1 is also designed to be efficient with power. It transmits data at a very low rate compared to modern communication systems, but this low rate allows the signal to be detected more easily over long distances. The spacecraft also uses error correction techniques, which means that it sends extra information along with its data, so that errors caused by noise or interference can be corrected when the signal is received. This ensures that the data sent by Voyager 1 can still be understood even after traveling for many hours through space. The onboard computer systems of Voyager 1 play an important role in its continued operation. These computers are not as powerful as modern computers, but they are reliable and were designed specifically for the tasks they need to perform. They control the spacecraft's systems, manage its instruments, and handle communication with Earth. The software running on these computers has been updated over time to fix problems and improve performance. Engineers on Earth have developed ways to send new instructions to the spacecraft, allowing them to adapt its behavior as conditions change. The spacecraft's ability to maintain its orientation is also critical. Voyager 1 must keep its antenna pointed toward Earth in order to send data. It uses a system of sensors and small thrusters to control its orientation. The sensors detect the positions of stars and the Sun, allowing the spacecraft to determine its position in space. The thrusters can then be used to make small adjustments to keep the spacecraft properly aligned. This system has been carefully managed to ensure that it continues to function, even as the supply of fuel decreases over time. Fuel management is another important factor in the spacecraft's long life. The thrusters that control its orientation use a limited supply of fuel, which cannot be replenished. Engineers have carefully controlled the use of this fuel, making only the necessary adjustments to maintain the spacecraft's orientation. They have also developed techniques to reduce the need for adjustments, such as allowing the spacecraft to drift slightly before correcting its position. This careful use of fuel has allowed Voyager 1 to continue operating for far longer than originally expected. The instruments on Voyager 1 have also been managed in a way that extends their useful life. Some instruments have been turned off to save power, while others continue to operate and send valuable data. The instruments that remain active are those that can still provide useful information about the environment through which the spacecraft is traveling. These instruments measure things such as magnetic fields, charged particles, and cosmic radiation. The data they collect helps scientists understand the region beyond the influence of the Sun. Temperature control is another challenge that Voyager 1 has managed successfully. In the cold environment of deep space, temperatures can drop to extremely low levels. The spacecraft uses insulation and heat from its power system to keep its components within a safe temperature range. As the power output decreases over time, less heat is available, which makes temperature control more difficult. Engineers have responded by turning off some systems to reduce heat loss and by carefully managing the remaining heat to keep critical components warm. The success of Voyager 1 is also due to the work of engineers and scientists on Earth, who continue to monitor and manage the spacecraft. They receive data from the spacecraft, analyze its condition, and send commands to adjust its operation. This ongoing support has allowed them to respond to problems and find solutions that keep the spacecraft functioning. Over the years, they have developed new techniques and strategies to deal with the challenges of operating a spacecraft at such great distances. The long travel time of signals between Voyager 1 and Earth presents another challenge. It takes many hours for a signal to travel from the spacecraft to Earth, and the same amount of time for a command to travel back. This means that engineers cannot control the spacecraft in real time. Instead, they must plan their actions carefully and send commands that the spacecraft will carry out on its own. The spacecraft's systems are designed to handle this delay by operating autonomously and responding to certain conditions without immediate input from Earth. The durability of Voyager 1 is also related to the environment through which it travels. While space is a harsh environment in many ways, it is also free from some of the factors that cause wear and damage on Earth. There is no air to cause corrosion, no weather to erode surfaces, and no biological activity to break down materials. This means that many parts of the spacecraft can remain in good condition for a long time. However, the spacecraft is still exposed to radiation and small particles that can cause damage, so its design had to account for these risks. Radiation shielding is an important part of the spacecraft's design. The electronics and instruments are protected by materials that reduce the impact of radiation. This helps prevent damage to sensitive components and reduces the risk of errors in the data. The spacecraft systems are also designed to detect and recover from certain types of errors, allowing it to continue operating even if it is affected by radiation. Another factor in the spacecraft's long life is the careful testing that was done before its launch. Engineers tested the spacecraft systems under conditions that simulated the environment of space. This allowed them to identify and fix potential problems before the spacecraft was sent on its journey. The knowledge gained from these tests contributed to the reliability of the spacecraft and its ability to operate for many years. The design of Voyager 1 also includes a high level of flexibility. The spacecraft was built to perform a specific mission, but it was also designed in a way that allows it to continue operating beyond that mission. This flexibility has allowed scientists to use it for new purposes as it travels farther from the Sun. The ability to adapt the spacecraft's operation has been an important factor in its continued usefulness. The data sent by Voyager 1 is limited compared to modern standards, but it is still valuable. The spacecraft sends information about its environment, which provides insights into regions of space that have not been studied before. This data helps scientists understand the conditions beyond the influence of the Sun and contributes to knowledge about the broader universe. The fact that this data continues to be received after so many years is a result of the careful design and management of the spacecraft. The continued operation of Voyager 1 also depends on the ground systems that receive its signals. Large antennas on Earth are used to detect the weak signals from the spacecraft. These antennas are part of a network that is designed to support deep space missions. The equipment used to receive and process the signals has been upgraded over time, improving its ability to detect faint signals. This has helped extend the period during which Voyager 1 can be tracked and its data can be received. The collaboration between different teams and organizations has also played a role in the spacecraft's long life. Engineers, scientists, and technicians work together to monitor the spacecraft, analyze its data, and develop strategies to keep it operating. Voyager 1 is no longer inside the protective bubble created by the Sun. That region, filled with solar wind and magnetic influence, was once its environment, but now it has passed beyond that boundary. The space it now travels through is known as interstellar space. This region contains very thin gas and dust that exist between stars. The density of material here is extremely low, yet it is still enough for scientists to study. As Voyager 1 moves forward, it continues to send back small amounts of data that help scientists understand this distant region. The direction of Voyager 1's travel is fixed relative to the Sun and nearby stars. It is heading toward a region of space in the direction of a group of stars that lie many light years away. However, even though it is moving very fast by human standards, the distances between stars are so large that it will not come close to any star for a very long time. Its journey is measured not in years or centuries alone, but in thousands and even tens of thousands of years. Over the next few thousand years, Voyager 1 will continue to move farther away from the Sun. The signal it sends back to Earth will grow weaker as the distance increases. Eventually, there will come a time when its power supply will no longer be able to support communication. The energy that powers its instruments comes from a source that slowly loses strength over time. As the years pass, more and more systems on the spacecraft will shut down. First, the scientific instruments, then the communication systems, until finally it will fall silent. Even after it stops sending signals, Voyager 1 will still continue its journey. It will become a silent object moving through interstellar space. There will be no further contact with Earth, but its motion will not change. It will keep traveling along the same path, guided only by the gravitational influence of stars and other massive objects it may pass near in the distant future. In about 40,000 years, Voyager 1 will pass relatively close to a star known as Gliese 445. This star lies in the direction of the constellation Camelopardalis. The distance of this approach will still be very large by human standards, measured in trillions of kilometers. Even at its closest, Voyager 1 will not enter the star system or orbit the star. It will simply pass by, continuing on its path through the galaxy. During this long journey, the spacecraft will experience conditions that are very different from those near Earth. The temperature of space is extremely low, close to absolute zero. The spacecraft's materials will slowly age under the influence of radiation and tiny impacts from particles of dust. These effects happen very slowly, but over thousands of years, they will change the condition of the spacecraft. Its outer surfaces may become worn, and some parts may degrade, yet the overall structure will remain intact for a very long time. Voyager 1 carries with it a record of life and culture from Earth. This record is attached to the spacecraft and is designed to last for a very long time. It contains information about the planet, its people, and its environment. As the spacecraft travels through space, this record goes with it, moving farther and farther from its place of origin. The chance that it will ever be found is extremely small, but it remains part of the spacecraft's journey. The path of Voyager 1 is also influenced slightly by the gravitational pull of objects in the galaxy. Although space is mostly empty, there are still stars, gas clouds, and other masses that exert small forces. Over very long periods of time, these forces can change the spacecraft's direction slightly. These changes are very small and happen slowly, but over tens of thousands of years, they can alter the exact path it follows. As it continues to travel, Voyager 1 becomes part of the larger motion of the galaxy itself. The Sun moves around the center of the galaxy, and Voyager 1 shares in this motion to some extent. This means that its path is not a straight line in a simple sense, but part of a larger, more complex movement that involves the entire solar system and the galaxy. Over hundreds of thousands of years, Voyager 1 will drift farther away from the region of space where it began. The stars that are visible from its position will slowly change. Constellations as seen from Earth will no longer have the same shapes when viewed from the spacecraft's distant location. The sky around it will appear different, shaped by its new position in the galaxy. The spacecraft will continue this journey for millions of years unless it encounters a significant force that changes its path. Such an event is very unlikely given the vast emptiness of space. Most likely, it will travel undisturbed, moving through interstellar space as a small object among countless others.